So this one is the one for methane. So it's more or less the same thing that we were just talking about. But one of the complicating factors is the reforming. So we're reforming the methane, we're forming CO and hydrogen. And just like in the flow sheet model, we had to think about both the composition of the gases going into the stack as well as the equilibrium of those gases coming out of the stack. So we're doing that again. And so that the same section that appears in that spreadsheet also appears here. We're solving the steam methane and water gas shift equilibria for the gases going into and out of the stack. And then just like on the other spreadsheet, I have an energy balance section where I'm looking at the overall energy balance on the stack and determining how much airflow we would need to keep the stack cool. I'm slicing the cell up again into 20 elements and doing a mass and energy balance along each one. The only thing that's changed is that we've added more species. And so part of this is at each point in the stack, not just at the beginning and the ending, we have to solve steam methane reforming and water gas shift equilibrium at each slice through the whole stack. The way I'm doing that in this model is the same way as I was solving voltage versus current. I'm using the Newton-Raphson method. In this case, I'm guessing phi, which is that amount of methane conversion from it spans 0 to 1. And I'm iterating the steam methane reforming equilibrium. We want to drive the log of K over Q to 0. And we're doing that by adjusting this number phi. So it's got a guess phi, and then it goes through a series of calculations. Of course, at each guess, you have to recalculate the molar flows, you have to recalculate mole fractions, etc. And just to save space, I've shrunk the width of all of those cells to a very narrow, so you don't even see them, but this is just showing the guesses and how the guesses evolve. So guess 1, guess 2, guess 3, guess 4, and you can see eventually phi converges on a solution, and we can check to make sure that it's actually obeying equilibrium at every point by looking at K over Q. So here is the log of K over Q for the steam methane reforming reaction at each of these positions, and it has been driven to 0. The other thing you can look at, this is calculating the equilibrium cell voltage based on all of these different species, hydrogen, CO, and CH4, using the delta G of formation for every species. And indeed, you're getting the same number using any of the species. And then also this is showing what is K over Q for both the water gas shift and steam methane reforming reaction equilibria. Should be 1 everywhere, and it is. So once it's converged on the water gas shift equilibria, then it does the rest the same way as it did the hydrogen stack. We calculate, we guess a current, and we use the Newton-Raphson method again to calculate current density as a function of position. This also gives us the two electron extent, which we can use to calculate the oxygen flow, and that feeds back into the mass balance and so forth. And so by the end of it, we can check, did it obey the mass balance? Did it obey the energy balance? The answer is yes. And then finally, the last thing it checks is K over Q for the coking reaction. As you'll recall, that number has to stay below 1 to ensure that we're not going to precipitate solid carbon somewhere in our stack, which we want to avoid. This tells us whether or not we fed enough water into the stack. And you can see that the problem is worse at the beginning. That's where coking tends to happen. And so the net result looks like this over here. We can look at the local stack temperature as a function of position, what the current density is doing as a function of position, and make adjustments as we need to from here.